and welcome back. The objectives of today's lecture are to introduce some linear algebra concepts that you're going to need in order to estimate robot pose and to use forward and inverse kinematics in order to estimate robot position or in order to send a certain velocity to the robot in order to move to a certain pose. So the objectives of today's lectures are to review vectors, including scalar and dot products, to review matrices, operations, and properties, and to review matrix transformations, including rotation and translation. So a vector is an array of numbers that is used to describe an n-dimensional space. In the context of mobile robotics, our configuration space, when we're talking about wheeled mobile robots, is typically two-dimensional, where we're looking at x, y, but theta is our rotation. So our vectors are typically going to be x, y, theta, which represents the position and rotation of a mobile robot within a global reference frame. For a vector, you're going to have A1 and A2, and you can represent that as A1x plus A2y, and the magnitude of a vector would be the square root of A1 squared plus A2 squared, and the angle theta would be the arctangent of A2 over A1. When you're scaling vectors, it changes the length of the vector, but it does not affect the angle. So for example, if you multiply A by the scalar K, it would be K times A1, A2, or written as KA1X plus KA2Y. And now the magnitude is the square root of KA1 squared plus KA2 squared. However, the rotation, the angle does not change, so it would still just be the arctangent of A2 over A1. When you add vectors together, you put them in a head-to-tail arrangement. So if I have a vector A and a vector B, then to sum them, C would be equal to A plus B. Vector addition is commutative, so I could also write that as B plus A. And when you look at that in terms of the matrix, then you would have a 2-by-1 matrix where the first element is A1 plus B1 and the second element is A2 plus B2. Or I could write it as C equals the quantity A1 plus B1x plus A2 plus B2y. The dot product of vectors, or the inner product of vectors, is a scalar. And it is written as A dot B or B dot A, which means that it is a commutative property. And it is the summation of the product of the element by element product. So it would be the summation of I, AI, BI. If the length or magnitude of a vector is 1, then we can say that the dot product of vector A and B will end up being the length of the projection of vector B on the direction of A, as shown in the figure here. Linear dependence looks at vectors and whether they are dependent upon each other. So for example, we would say that vector B is linearly dependent on vector A if B is created from scaling and summing of A vectors. So for example, B would be equal to the summation of I, Ki, Ai. So essentially, if I multiply all of vector A by K and then add them together and I can create B, then we say that they are linearly dependent. However, if there is no combination of gains Ki that creates B from the elements of A or from the vectors A, then we say that these vectors are linearly independent. And this concludes today's lecture on a review of linear algebra concepts related to vectors. Make it a robotacular day!